Hi again, I'm Aki.
And I am Kurubi.
We followed K3MT's method and drew a Smith chart.
Mike said it's a chart of how impedance changes along a transmission line. Changes depend on the line's characteristic impedance, Z0. So you need to record it.
To start, set it at 50 ohms, a very common value. Then any impedance with resistance equal to 25 ohms will be plotted somewhere on this 0.5 circle. And one with resistance of 50 ohms will fall on the 1 circle. The same holds for any other value of resistance from 0 to infinity.
An impedance, of course, is a resistance in series with a reactance. An inductive reactance of 25 ohms plots on the upper 0.5 arc. Since it is half of Z0. And one with 50 ohms of inductive reactance plots on the upper 1 arc.
Similarly, any inductive reactance from 0 to infinity can be plotted on an upper arc. Negative reactance, from capacitance, plots on the arcs below the horizontal line. 25 ohms negative plots on this arc. And negative 50 ohms here.
Any other negative, or capacitive reactance can be plotted similarly. The horizontal line is a case of no reactance. It's called the real axis. Here's an impedance of 50 ohms resistance and 50 ohms inductance. It plots on the 1-1 circle and arc.
Now look at a half-wave dipole with a perfect 1-to-1 balun. Its impedance is 75 ohms, unbalanced. Z0 is still 50 ohms. So this plots on the chart on the R equals 1.5 circle, and the real axis.
Get the circle's diameter by reversing Mike's instruction. Add 1, then invert the number. Its diameter equals 1 over 1.5 plus 1, or 4/10. This is the added red circle.
When coax is added, the impedance at its other end changes, and depends on the amount of coax, in wavelengths, or degrees. 90 degrees is a quarter wave.
To see what happens, draw another circle in the center that touches the R equals 1.5 circle. These center circles are circles of standing wave ratio. This one has SWR equals 1.5 to 1. The two circles Mike drew are at SWR equals 2 to 1, and SWR equals 3 to 1.
If the coax is 1/8 wave long, or 45 degrees, the impedance moves clockwise twice that amount on the chart, toward the source, your transmitter. It moves along at constant SWR, from the 90-degree mark, to the 135-degree mark.
Why? Because we were worried about reflected power. That travels from one end of the coax to the other, and back.
The normalized impedance becomes nearly 0.9, minus J 0.3. The impedance then is close to 45 ohms, with 15 ohms of negative, or capacitive reactance.
At a quarter wave long, the impedance becomes 33 1/3 ohms. And no reactance. You may recognize this as a quarter wave Q section.
At 3/8 wave long, the impedance goes farther, near to 0.9 plus 0.3. It's now inductive. And at a half wave long, the impedance returns to its starting point.
Let's do another antenna. A wire dipole 3/4 waves long. Some measured data say its impedance is Z equals 800 plus J 600 ohms. I'll use 300 ohm ladder line.
So the Z0 notation is changed to 300. And I'll divide the Z values by 300 to normalize them. The impedance is plotted near Z equal 2.7 plus J2. It's inductive.
Drawing a SWR circle through the impedance shows an SWR of about 5. Making the line 100 degrees long brings the normalized impedance to 0.2. Non-reactive.
Thus Z equals 60 ohms. A decent match to a 50 ohm transceiver. All you need is a 1-to-1 balun.
This concludes our demo. You will find it and lots more in Mike's book. As of March 2022, sold by these dealers.
If you can't find it, contact Mike. So till next time, this is Aki
And Kurubi,
saying thanks for watching. Bye, for now.